Hi guys, so I told you that I was going to put a video up and that it would be only 10 to 11 minutes in length. So I am going to go as fast as I possibly can so that way I can get all the information that I can in 10 to 11 minutes, since that's what I told you the length of this video would be. So I posted the slides up on the blog that correspond with with this video, and this is over nuclear chemistry. Now today in class, I showed you that second slide, because the first slide is just the title slide. But I showed you the second slide about nuclides and how protons and neutrons, we can also call them nucleons. So nucleons just mean that they are part of the nucleus. So it consists of two different ones. We could have protons or neutrons, and those are the nucleons. Now, the third slide, guys, talks about isotopes. We already know about isotopes, you've already learned about those, but really radioactivity has a lot to do with isotopes, and we are going to focus a lot on that tomorrow as we talk about nuclear decay and half-lives. But I really want you to skip over radioactivity, so skip over slide number 4. I want you to look at slide number 5. On slide number 5, I've included the 3 main types of radioactive decay. So on slide number 5, these are the 3 main types of radioactive decay. The first one that you see on here is called an alpha particle. And an alpha particle is the same thing as a helium atom. Alpha particle is the exact same thing as a helium atom. So alpha particle is one way that we can say it. This little crazy fish is another way that we can also symbolize it. And then helium is another way that we can represent an alpha particle. And this would be the nuclide for helium. So you know that you have your symbol, mass, number. Very good. So we have our symbol here, there's the mass, and then there's the atomic number of protons. So all an alpha particle is a helium nucleus. That's it. It's the same thing as a helium nucleus. Beta particle is something that's a little different. And a beta particle, or beta decay, a beta particle is where in a reaction, in a nuclear reaction, we have some type of electron that's given off. So a beta particle is simply just like a really high energy electron. So we can symbolize the beta particle with this little Greek symbol, just B for beta, it's a beta particle. We can also symbolize it by writing this. We have E, just to represent electron, because it's just a high energy electron. And then we can write it like a nuclide, and I'm going to explain a little bit more what this means when we do a type of decay, but I just want you to understand that this is a way that we can also write it, and that's on your slide too. It says the 0, 1, and then the E. The last type of decay is called gamma decay, and gamma decay is represented by this little symbol, so this would be gamma. And gamma decay happens when we release some type of photon. So typically photons are massless, and they oftentimes look a lot like light. So very often we would see light being emitted. So there's 3 different types of nuclear decay, 3 major types, I should say, because we're going to talk about a few exceptions, or a few other little small types, not exceptions. First one that we'll talk about is alpha, and alpha particles are the same things as helium nucleus. So a helium nuclei is the same thing as an alpha particle. The next thing is beta decay, and beta decay is a type of nuclear decay that's given off, or that happens when an electron is lost from an atom. And then gamma decay is where we lose some type of photon, or some really high amounts of electromagnetic radiation is given off. I want to look at some of these examples so that way we can use all of them. The next slide just talks about like the penetrating power of all of these particles, or those 3 specific major types of decay. An alpha particle or alpha radiation doesn't have a very large amount of distance that it can cover. So tomorrow I'm going to try to show you with the Geiger counter exactly the very small amount of distance that alpha particles actually reach. They typically will only reach an inch. They also can't pass through or penetrate through a piece of paper. They also can't penetrate in terms of your body through your skin. A beta particle, or beta decay, or beta radiation, it can penetrate up until like a piece of metal. Specifically, lead would be something that would block it, but a nice strong kind of thicker piece of metal would also block a beta particle. Now beta can go through your skin, but it's not going to go any more underneath your skin, like towards your blood cells and towards things like that. So it's not going to mutate any of your cells, any of your DNA. It won't do any kind of damage like that. But it can go through your skin. It's just not going to go any farther than that. Gamma radiation is a type of radiation that will go through our skin, goes through all the way up into our cells, can mutate our DNA, and it's actually very damaging to us. It is a potential cancer-causing agent. Well, it is a cancer-causing agent because it can mutate or change how our DNA looks in our cells. So gamma radiation has the most penetrating power. Beta would be like the middle ground, and then alpha would have the least. So I just want you to know in terms of like really how effective they are in terms of penetrating power for radiation. Okay, next slide. This is slide number 7. On slide number 7, it's starting to talk about alpha decay. And I want you to understand that alpha decay just means that an atom or some type of element is emitting or losing an alpha particle. So I gave you an example on this slide, and I wrote uranium-238. So I have uranium-238. We know it's the atomic number 92. When it goes through an alpha decay, it loses an alpha particle. And I can symbolize an alpha particle with a helium nucleus. So we can just write a helium nuclide. But this uranium doesn't just emit this and turn into this. When we do a nuclear reaction, we have to account for the rest of the mass and the rest of the protons. So I have a mass of 238. This uranium isotope became really unstable, and it needed to emit this alpha particle to try to stabilize itself. So I have uranium-238, it lost this helium, it lost 4 of its mass. So something else needs to fulfill this equation because I need to add up the masses to where they would equal 238. So if this is 238 and I have 4 on the other side, so I really think about this like an equal sign. So something plus 4 equals 238, would be 234. And now I had 92 protons over here, but because uranium emitted an alpha particle, it lost 2 of these protons. So it changed into a totally different element because it lost 2 protons. Because it lost those 2 protons by emitting a helium nucleus. So because it emitted a helium or alpha particle, lost 2 protons. So I need to have a total of 92 protons accounted for over here. Because I have a total of 92 protons over here. So I need something plus 2 to make 92. So that would be 90. So now if I add this 90 plus this 2, I get 92. On the other side I have 92. If I add my 234 and my 4, I get 238. And on the other side of the reaction is 238. So everything is balanced. But I need to figure out what element this is. I can figure out what element this is by looking up what number or what element has the atomic number 90. And if you look that up, you would see that it is thorium, which is TH. So that's how you would do an alpha reaction, an alpha decay reaction. So I just want to review this one more time. So on our reaction, we had uranium, and uranium had a mass of 238 and has an atomic number of 92. In an alpha decay process, uranium-238 is really unstable. So because of that, it's going to lose an alpha particle, which just means it's going to emit some type of helium nucleus. So uranium is going to break down into emitting this helium nucleus. So I see that here. But it can't just do that. It has to account for all of this extra mass and all of these other protons that it has. So we always want our nuclear reactions to be balanced. We always want everything to be balanced. So in this reaction, if helium has a mass of 4, and I originally started with 238, then I need to account for that leftover mass. So that leftover mass was 234, because 4 plus 234 equals 238. Now, helium has 2 protons, so because it has 2 protons, I need to account, though, for 90 more, so that's where we got this 90 from. So if I add those two together, the 90 plus 2, that gives me 92. So that means on this side of the reaction, I have 92 protons. On this side of the reaction, I have 92 protons, so those are good. On this side of the reaction, I have 238 for my mass number. On this side of the reaction, I have 4 and 234, which gives me 238. So that means that this side of the reaction in terms of mass number is balanced. So that's how we do an alpha decay. For beta and gamma, we'll look at those tomorrow in class after we do our half-lives, but I at least wanted to get us started on the types of nuclear decays, the major types, as well as how to do an alpha decay. So please make sure that you take some good notes. If you have questions, comment on the blog. Also bring those questions to class with you tomorrow. And don't be surprised if you have an index card awaiting you whenever you get into class tomorrow. Bye guys, have a good night.